Hello there. So this is video number 1 of section 6.4. And basically this entire video will be dedicated to answering the question on the board behind me. How do we transform a non-orthogonal basis into an orthogonal basis? So I have these listed out in the notes, but I'll just sort of remind everyone, we like orthogonal bases for a variety of reasons. So we've seen that, if we have an orthogonal basis for a subspace, remember one of the key components of a basis is that, we can write every vector in our subspace W as a linear combination of, vectors in the basis, and, calculating those dependence relations is really easy. Remember, calculating those coefficients attached to the basis vectors just involves sort of a fraction of a couple dot products. I think that was theorem 5, I want to say. We've seen now in the last couple sections that if we've got this orthogonal basis for a subspace, we can use that basis to calculate the shortest distance from any vector to the subspace, which we will use a lot again in the next 2 sections. And then it's also easy to turn an orthogonal basis into an orthonormal basis, and in quite a few applications, like I said, to computer algorithms, eigenvalues and such, you want to be working with orthonormal bases, or even more than that, matrices with orthonormal columns. So basically this section is just going to be dedicated to taking a non-orthogonal basis, transforming it into an orthogonal basis, and then next video we'll actually go one step further than that, and we will go over how to transform a non-orthogonal basis actually into an orthonormal basis. But I wanted to start with an example in R3. So we're given this subspace W spanned by x1 and x2. These 2 vectors are linearly independent, and you could quickly take the dot product to determine these vectors are in fact not orthogonal. So we need some way to find an orthogonal basis. So we want an orthogonal basis V1, V2 for W. Now, there could be potentially a few ways to do this in this sort of a setting, especially where W has dimension 2, so there aren't that many vectors. If you kind of guessed and checked enough, you might be able to find one. What we're going to do this video, though, is sort of introduce a process which, actually, as we'll see in the next example, works for any subspace of any dimension and sort of provides a nice outline for an algorithm for how to do this. So if I'm going to construct an orthogonal basis that spans the same set W as this original basis x1 and x2, it might actually make sense to just let the first vector in this basis be the first vector in the original basis, right? So remember, all we're trying to do is find a set of vectors such that the dot product of all of these vectors is 0, right? So I want to find 2 vectors, v1 and v2, whose dot product is 0, that I can kind of guarantee span the same set as x1 and x2. And as long as I haven't added a vector to the set yet, probably makes sense just to start with the first vector. All right, so I found one. Now comes the hard part, right? I need to find a vector v2 that is orthogonal to this vector v1 slash x1, 3, 0, negative 1. So I need to find some vector that will help me span the same set as x1, x2, and will be orthogonal to v1. Now maybe there's a vector that is orthogonal to v1, and maybe is a linear combination of v1 and x2. Well, notice if I take the projection of, and I want to make sure I get this right, x1 or x2 onto v1, right? So this is, in a sense, the scalar multiple of v1 that is closest to x2. And if you'll remember, this is v1 dot x2 divided by v1 dot v1 over v1, or times v1, excuse me. And of course, we know that here v1 is equal to x1, but as you'll see moving forward, we kind of start to use this notation because we're in a sense changing the set. So this vector itself isn't orthogonal to v1. But remember, by the orthogonal decomposition theorem, if I let P be the vector x2 minus the projection of x2 onto v1, then P is actually orthogonal to v1. And so this just follows directly from the orthogonal decomposition theorem. So now we just have to check that if I let P, and actually I'm just going to go ahead and call this v2. If I let v2 be this vector, x2 minus the projection of x2 onto v1, will it span the same set as v1, v2? Well, yes, right? Because will v1 and v2 span the same set as x1 and x2, right, is the question. And the answer is yes, because notice here, v1 is x1. v2 I've written as this linear combination of x2 and technically x1, right? This is technically a scalar multiple of v1, x1, whatever you want to call it. So this set will span the exact same set as W because hidden in each of these two vectors is each of these two vectors, right? So I know that v2 and v1 are orthogonal, linearly independent, and ultimately just linear combinations of my original basis vectors. So now v2 is just a simple few vector operations away. So it's x2 minus the projection of x2 onto v1. So v1 dot x2 is equal to 3 times 8 plus 0 times 5, or just 0, plus negative 1 times 6 over v1 dot v1, so 3 squared plus 0 squared plus negative 1 squared times v1. And so this is equal to the vector 8, 5, 6 minus 9/5 times 3, 0, negative 1. And working through some fractions, you can actually get that v1 is equal to v2 is equal to 13/5, negative 5, 39/5. So there's v2, there's v1. And so notice v1 and v2 are orthogonal. And as I've already explained, the way we generated this vector v2 means that the span of v1 and v2 is equal to the span of x1 and x2. So these two vectors, v1 and v2, form an orthogonal basis for the same set W that was originally spanned by basis x1 and x2. So we can sort of now continue to apply this idea of orthogonal projections to not only, kind of finding this closest distance, but also taking a basis, as we just saw, and transforming it into an orthogonal basis for the same set. So this was with two vectors. I want to, if I can get through this, show an example of how it works for three vectors. And I think in this example of how this process works for three vectors, you'll see why it is just completely unrealistic to ask anyone to ever do it by hand for more than three. Because as you'll see, this process can get a little tedious. But we'll do it. So We'll call this example 2, I guess. So we're going to let x1 be the vector 1, 1, 1, 1. x2 be the vector 0, 1, 1, 1. I think. Let me double check. Yep. And x3 be the vector 0, 0, 1, 1. So let W be the span of these three vectors. We'll allow ourselves to assume we could show this, but we'll just sort of take it on assumption that these three vectors are linearly independent. And so we want to transform, or we want to find, I guess, using these three vectors, an orthogonal basis. V1, V2, V3. For W. All right, so let's jump into it. So again, we've started off with these three vectors that are not orthogonal. We want to find three vectors that are orthogonal that we know will span the same set as our original three vectors. So basically the way we're going to do this is we're going to take it one vector at a time. So we're going to find a vector v1 that will span the same set as x1. Then we're going to find a vector v2 so that v1 and v2 will have the same span as x1 and x2. We've already seen how to do that. And then finally we're going to find a vector v3 that has the same span as x1, x2, x3. So much like before, in this new orthogonal basis we're finding, we're just going to let v1 equal x1 equal 1, 1, 1, 1. If we haven't added a vector to our space yet, there's no use in trying to be fancy. Just take the first vector we have. All right, so unfortunately, that is by far the easiest step. So we're actually going to find v2 in the same way that we did before. So we're going to let v2 be the vector x2 minus the projection of x2 onto v1. So remember, we've already shown this vector will be orthogonal to v1 based on the way we're calculating it. And then after we calculate this, I'll explain what we have so far and why what we have so far is going to work for the purposes of this problem as a whole. So this is the vector 0, 1, 1, 1, 1 minus v1 dot x2 over v1 dot v1 times v1 All right, so I might, just to shorten things, notice here v1 and x2 are both relatively simple dot products to calculate. So notice v1 is just the vector 1, 1, 1, 1. x2 is the vector 0, 1, 1, 1. So the dot product of v1 and x2 is equal to 3. The dot product of v1 with itself is equal to 4. And then multiplied by v1. And so this gets us vector v2, which is negative 3/4, 1/4, 1/4, 1/4. But I don't like fractions, right? So if you remember, the dot product is actually not affected by scalars. Well, it is affected by scalars, right? But basically, when we multiply a dot product of two vectors by a scalar, remember, we can pull the scalar out of that dot product. So if this vector v2 and v1 are if the dot product of these two vectors, right? So if v1 dot v2 is equal to 0, then v1 dot c times v2, where c is any scalar, is also equal to 0, right? Because remember, I'm allowed to pull this scalar out and wind up with the original dot product. So what I'm going to do is I'm not going to use this vector with all these fractions. I'm actually going to use the vector I just calculated multiplied by 4. And notice v1 and v2 are still orthogonal. And so what we have so far to this point is two vectors v1 and v2, so that the span of v1, v2 is equal to the span of x1, x2. And this is because of the way we did our previous problem, right? Where basically we did our previous problem in the exact same way we did this, and had that this was the case when we only had two vectors. So basically up until this point, we've just been ignoring x3 and v3, and we've found two vectors so far whose span is the same as the first two original vectors. So now we just need to find a vector x3 whose span is the same as x1, x2, x3 when I add it to the set v1, v2. But much like we calculated v2, we're going to use our knowledge of orthogonal projections to calculate the vector v3. So I'm going to let this subspace, I'll call W2 the span of v1, v2. So then, if I let v3 equal x3 minus the orthogonal projection of x3 onto W2, well, by the orthogonal decomposition theorem, this vector is orthogonal to both v1 and v2. And again, notice the way I'm calculating all of these vectors are ultimately just linear combinations of my original three basis vectors. So these will ultimately span the same set while still being orthogonal. So why is this a hard problem? Well, if you'll remember from the orthogonal decomposition theorem, this is equal to the vector x3 minus x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 times v2. So now I have to subtract off two components, one related to v2, one related to v1, and one related to v2 from x3 in order to find this orthogonal vector. And so as you can kind of see, even with three vectors, this process can get somewhat lengthy, because while this is going to work and we're going to get an orthogonal vector, we have to calculate a lot of dot products. So, doing this, 0, 0, 1, 1, minus the dot product of x3 and v1 is 0 times 1 plus 0 times 1 plus 1 times 1 plus 1 times 1, so 2, over v1 dot v1 is 4 times the vector 1, 1, 1, 1. The dot product of x3 and v2, that'll be a little harder to calculate, so this should be 0 times negative 3 plus 0 times 1. Actually, that wasn't too bad. 1 times 1 plus 1 times 1, all over the dot product of v2 with itself, so negative 3 squared plus 1 squared plus 1 squared plus 1 squared times v2. And so this is equal to the vector 0, 0, 1, 1 minus 1 half, 1 half, 1 half, 1 half, minus 1 over 6 times negative 3, 1, 1, 1. And doing all of this vector arithmetic, you should get that this is equal to the vector 0, negative 2/3, 1/3, 1/3. And so, again, because maybe I don't like fractions, I can take any scalar multiple of that vector, and I'll let my last vector be 0, negative 2, 1, 1. So, using the exact same process, I'll circle the 3 vectors that give us our solution here. v1, v2, and v3 give us an orthogonal basis for W, where W was the set spanned by these 3 vectors. So, as you can probably see, this is a little bit of a lengthy process, and as we'll see in a second when I state sort of the main theorem, which says that this was in fact the correct way to do it, and this in fact can be generalized to basically any set of vectors, it's a lengthy process. And so, beyond 3 vectors in a basis, you probably never want to do it by hand. Because each new vector you add, you have to add an extra term when calculating this sort of orthogonal vector, which is helping us to span the same space. But so it turns out that the 2 examples we just went through, the process has a name. It is called the Gram-Schmidt process. And it tells us how to take any basis for a vector space and, using that basis, construct an orthogonal basis for the vector space. So, given a basis, which we'll call x1 through xp, for a non-zero subspace, I guess this problem is a little bit trivial if it's a 0 subspace, right? Because then 0 would just be an orthogonal basis, I guess. We're going to let v1 equal x1, much like we did before. We'll let v2 equal x2 minus x2 dot v1 over v1 dot v1 times the vector v1. I'll go one more term out. v3 will equal x3 minus x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 times v2. And basically, for each vector, just continue this trend of subtracting off one more term using the previous vectors you found. So in this way, v sub p will equal x sub p minus x sub p dot v1 over v1 dot v1 times v1, all the way out to x sub p minus 1, or sorry, x sub p dot v sub p minus 1 all over v sub p minus 1 dot v sub p minus 1 times v sub p minus 1. So again, basically subtracting off this identical term for each added vector to the basis. Then, and maybe I'll write the remaining, then the basis we calculate in this way, v1 through vp, is an orthogonal basis for w. But on top of that, we kind of showed this in the previous example. If I take the first k vectors in this set, so v1 through vk, that span is always equal to the span of the first k vectors in my original set for all k from 1 to p. So what this means is that basically at every point that I found a new vector v sub k as I'm increasing here, basically the set of, this, I'm basically keeping the span sort of intact in this way in that order. And so again, this is what we did for up to 3 vectors, but repeating that same process for more, you can do it. Don't do it by hand for more than 3 though. Not recommended. All right, so that is the first video. So the next section we will see how we can use this sort of a process to now find an orthonormal basis. So get ready to do some square roots.